Welcome to the Donaldson Clean Solutions webinar, Water and Diesel Fuel. I am Jim Doyle, Senior Engineer at Donaldson. This webinar will run approximately 20 minutes. We hope you find this presentation interesting and informative. Water, water everywhere, nor any drop to drink, is the rhyme of the ancient mariner. Everyone is aware that water is not supposed to be in diesel fuel. Generally, water is not added to diesel fuel intentionally, but it can wind up being present in fuel systems and infrastructure. It contributes to a range of issues that relate to operability and costly repair or cleanups. The objectives for today are to describe how water gets into diesel fuel, define what water in diesel fuel is, cover why water in diesel fuel is an issue, cover what technologies are used to remove water, and finally best practices to reduce or prevent water from getting into fuel. So how does water get into diesel? This is a question with a not so straightforward answer. Diesel fuel at the time of refining is relatively dry. As it travels through distribution, sits in storage tanks, and resides in equipment, it can pick up moisture. In underground storage tanks, surface water can drain down into tanks if infrastructure is not designed and maintained to prevent this. Underground tank spill containment designs and conditions are critical to prevent water routinely entering the fuel tank from the groundwater or precipitation from above. Other sources may not be as obvious. In above-ground storage tanks and on-equipment tanks, breathers open to atmosphere allow outside air in that creates a situation that promotes condensation on tank walls above the fuel. The condensed water droplets can then run down the walls and begin to collect in tank bottoms. Onboard equipment tanks create a similar condensation condition, only more severe due to the warm fuel and much cooler tank walls in the headspace above the fuel. Think of an indoor pool with windows surrounding it covered in condensation. Fuel sitting in tanks can increase in relative humidity simply by cooling or eventually having free water drop out of the fuel, a process similar to the formation of clouds or fog in air. In very cold conditions, water can even begin to separate out of fuel as ice, collecting in the tank bottom, and when it melts, it becomes free water at the bottom of the tank as well. Water can take several forms in fuel and fuel infrastructure. Most people think of water in diesel fuel as visible droplets of water in the fuel. Generally as a glob of water at the bottom of a sample jar or a layer of water at the bottom of a tank, etc., like the image at the top left. This form of water describes what is generally referred to as free water, or in industry test standards, it is also called coarse water. Coarse water simply refers to the relatively large droplets of water in fuel. A term that has become more common lately referring to water in fuel is emulsified water. Emulsified water is simply very small droplets of free water suspended in fuel, similar to the sample at the bottom left. If fuel with coarse free water is run through a pump, the droplets of water will get chopped up by the pump. These small droplets are much more stable in the fuel than large free globs of water. They will stay floating around as very small droplets for long periods of time and are much more difficult to separate by traditional means than coarse water. The less obvious form of water is dissolved water. Dissolved water is the water that is present in fuel before it becomes visible as a haze, droplets, or a layer of water at the bottom of the sample. The top layer of the top left glass contains some water, but is not fully saturated and is still clear and bright. The sample at the top right, after shaking and some settling, shows the top fuel layer still cloudy at or above saturation. Think of this form of water like moisture in the air that becomes a cloud or fog when the air cools. It is also common to hear the term total water. This term is a combination of dissolved and free water, including emulsified water as well. A fuel sample with water in it, unless tested immediately, may give different results of dissolved and free water at the time of testing due to the changing conditions for the sample, so it is simply reported as total water. In the lower right image, I added some soap and shook things up. More on that later. At this point, it is worth taking the time to describe the ranges of water contamination and what standards look like for the industry. Industry standards for describing water and fuel can vary, but it is generally considered that fuel with 200 ppm or less water at 70 degrees Fahrenheit means the fuel should be fit for use. Fuel water separators and coalescers are generally tested at much higher water concentrations, about 2,500 ppm total water. These technologies address free and possibly emulsified water only, not dissolved water. Diesel fuel at the time it leaves the refinery is usually in the range of 70 to 100 ppm total water at roughly 70 degrees Fahrenheit. This fuel is considered about 50% saturated with water, meaning it can hold roughly 140 to 200 ppm of dissolved water before it reaches its saturation at 70 degrees Fahrenheit. Fuel in this range of saturation would appear clear to the eye and there would be no visible droplets of water like the center photo in the slide. As that fuel sample cools, without the addition of more water, it will approach a point where it is able to hold much less water and it would begin to appear cloudy. The fuel would then be considered at saturation. This is the case in the photo at the right. It will still not show any visible droplets, but further cooling could begin to drop free water to the bottom of the sample. Remember, cold fuel holds less water in saturation, so it becomes relatively more wet, much like clouds or fog forming in air as it cools. It's again worth mentioning that fuel cooled below 32 degrees Fahrenheit, freezing, will begin to have water crystals freeze out and they will settle to the tank bottom as solids. This can contribute to filter plugging as ice if conditions are right and they are drawn to a filter. Otherwise, they will settle and eventually melt when things warm up, creating free water at the bottom of the tank. Plain fuel in contact with the atmosphere at a constant temperature will not generally become more saturated. It will become more saturated if it is in contact with free water at the tank bottom or condensation is dripping in and the fuel is being sloshed around on equipment. Free water in bulk storage contributes to rust and corrosion of carbon steel infrastructure components. This can include steel tank bottoms, steel fittings in fiberglass tanks, submersed pump components, carbon steel pipes, tank sensors and measurement components, etc. Failure of these system components can be costly to fix. Leaks, equipment downtime, tank cleanouts, and repairs are expensive. Free water on equipment can also cause tank corrosion and microbial growth issues, but the main concern is the modern high-pressure common rail system components, like fuel injectors and high-pressure common rail pumps. The high-pressure pumps and injectors are very sensitive to corrosion, causing sticking and seizure of components, leading to costly repairs. These fuel system components are also vastly more sensitive to both soft and hard particulate contamination. The secondary effect of free water in fuel is microbial growth. Commonly referred to as bugs, it's generally bacteria and fungi, not algae. Algae need light to grow. Microbes need water and food to live. In fuel infrastructure, that condition generally occurs at the fuel and water interface near the tank bottom. This is known as the rag layer and is seen in the photo at the center. On equipment, good conditions may occur in the tank or in a filter. At the bottom left, you can see a water coalescer element that has microbes growing on it. The microbes eat the fuel, breaking it down and degrading fuel quality in general, but they need to live in the free water. If you have no free water, you have no bug problems. Both corrosion, chunks of rust and things, and microbial growth, chunks from the rag layer, create additional particulate in the fuel that will tend to plug filters and create operability issues. Another fuel usability issue associated with free water is the creation of filterable solids due to water's interaction with some of the fuel's additive package. Water tends to promote soft filterable formation with biodiesel, increasing chances of glycerin dropout, as seen on the right, and under certain conditions with cold weather and some other functional additive components. These all lead to faster plugging and solids formation in tank bottoms. The traditional and most common method of water management, free water management that is the use of coalescers and water separators. These technologies have been around for decades and have traditionally done a good job of free coarse water removal. They're in virtually every diesel engine system. They function by retaining or stopping water droplets for some time so other water droplets have time to run into them and coalesce into larger droplets until they get big enough to drain out of the media to to the bottom of the housing where they can then be drained off. Relatively recent chemistry changes have made this job more difficult. The introduction of ultra-low sulfur diesel has increased the need for fuel additives to ensure safe operation and protection of diesel fuel system components. The chemicals that are added are generally called surfactants, or surface active agents. They coat surfaces to protect things from rust, improve lubricity to prevent component wear, etc. They are very similar to soap and tend to reduce the ability of these technologies to separate water from fuel. Biodiesel blending also contributes to this challenge of water separation. Referring back to the example from earlier, a plain fuel and water mix will settle the free water out to the bottom in a short time. If you added some dish soap and stirred things up, the separation becomes much more difficult. It is the soap that allows the fuel to hold lots of water droplets and the water to hold lots of fuel droplets, making a complete separation very difficult. Another time-tested technique to manage water is the use of certain water management additives. Emulsifiers are used to increase the amount of water that the fuel will carry within it below saturation. The idea being that over time, free water will be drawn into the fuel as dissolved water, preventing its buildup in tank bottoms or equipment tanks, and it will maintain a drier fuel system on an ongoing basis. Another common option is to use a demulsifier, which is added to drive water out of the fuel and increase the effectiveness of water removal by coalescers or water separators. One other common type of water removal technology used mainly in fuel dispensing applications are water absorbers. Water absorbers are filters that have an ability to absorb free water from fuel into a material in the media called SAP, or super absorbent polymer. This technology has been in use for decades as well. It has only a modest capacity for water and is more of a means of detecting free water issues than dealing with an ongoing free water issue in the fuel supply. Finally, we'd like to look at best practices. What are the best ways to deal with water and hopefully avoid or reduce the impact of many of the issues covered here today? Historically, it was not a big deal to let diesel fuel be in contact with free water. It was more stable over time, engines were not nearly as sensitive, and it was reasonably easy to drain it off or coalesce it out just prior to use. As we have covered here, the chemical makeup of fuel has changed significantly, and the needs of modern diesel fuel engine systems have changed at the same time. Fuel is less stable in storage in the presence of water. It degrades in quality and creates various solids that can cause filterability and operability issues. Water can also directly damage infrastructure and engine fuel system components. At the same time, the technologies traditionally relied upon to deal with the water and remove it face bigger challenges to perform reliably. In daily practice, there are things that can be done and future decisions that can be made that can reduce the impact of water on equipment and operations. To reduce the condensation of water on equipment, it is recommended that fuel tanks be kept full and fill them at the end of operation rather than run and rest with substantially empty tanks. The smaller the headspace volume in the tank, the less area there is for condensation to occur. Similarly, above-ground fuel tanks that have large headspace volumes would tend to be more susceptible to condensation on interior tank walls, adding water that will settle to the bottom, leading to higher water content in the fuel. Keeping storage tanks full rather than empty on an ongoing basis will tend to minimize the moisture buildup. Underground tanks are somewhat less susceptible to condensation issues since the tanks are at a much more constant temperature than surface tanks, but they do have the potential for significant surface water ingress. Water leak points like the fill and spill containment system or groundwater intrusion in high water table situations are obvious concerns for these types of systems. Some large fuel tank farms have what is referred to as floating suction, and is becoming more common in practice. Floating suction draws fuel from the top layers of the tank rather than near the bottom. This is done to avoid the things that tend to settle over time, solids and water, so the fuel leaving the tank is as clean and dry as possible. Many fuel tanks do not have breathers. They may have screens or even open pipes allowing air and contaminants to enter freely. It is good practice to install breathers to prevent particulate and water ingress into systems where possible. Lastly, a common issue is the ability to drain water. the best practice possible for water contamination management is the ability to actually drain all of the water from a low point in the tank. Not the typical 3 to 9 inches above the bottom, but actually the low point of the tank. It only takes an inch or so of water for microbial growth to get going, and exposure to free water tends to cause other fuel solids formation. This is not an easy afterthought, but for new infrastructure, it is a best practice to design in from the start where possible. In conclusion, with the changes in fuel and engine technology, water management strategies need to evolve to be more proactive than reactive, or it is more likely that equipment operators will face the types of issues covered here. Adopting best practice strategies, maintaining and designing fuel infrastructure that minimizes water buildup will also reduce downtime in the future. Thank you again for taking the time to join us here for this webinar today. In closing, we ask that you check out our online resource, My Clean Diesel, and connect with us there.